we ended, we were looking at electrons and where they exist within individual atoms. So we've got the s and the p orbitals. After the p orbitals, what do we move to? D orbitals. After the d orbitals, we move to f orbitals. One of the things that's awesome about organic chemistry, we don't care about the d or the f orbitals. Completely irrelevant to our topics at hand-ish. There are a few exceptions where we'll talk about both phosphorus and sulfur with their d orbitals because it changes some of their chemistry. But for the most part, we settle in the s and the p orbitals. All right? So we need to be familiar with what they look like and then how these things can potentially interact with each other, because that's ultimately going to determine our bonding situations. This is organic chemistry, so also, unlike Gen Chem, we simplify a lot. We simplify excessively to a certain point. So we can look at the modified periodic table that will be given to you for every exam, so all except for the final. This modified table will show up, so you've got all this information. Okay. Within that, what patterns could we potentially pick up? Think back to your Gen Chem days. We're going to be pushing 151, which I know was a while ago. What trends come off the periodic table? We can look at electronegativities. Massively important item to be familiar with. Okay? Everybody needs to have some understanding of what's going on with your electronegativities. And we're looking at general trends being good enough. Okay? So what's our most electronegative? Fluorine is our most electronegative, and our least? It's a little bit weird if we use this periodic table. Okay. We can look at our lower left. Our potassium, if we jump to the big one, we're looking at our cesium or francium. Okay. Is that perfect? No, but it's pretty darn close. So it increases as you go up, and it increases, not that weird direction, as you go to the right. Okay. What else? What other things might you look at? And look at atomic size, which will come in handy. We will do a lot of stuff with size, and actually I'm going to change the order on this a little bit. Turns out atomic size probably a little bit more important than electronegativity. Okay. What do we know about size? 151.
Increases as we move down.
Okay, it gets bigger as we move down. Why would it get bigger?
Electrons further away from the nucleus.
Okay, the electrons move to further or higher energy orbitals. Those higher energy orbitals are further from the nucleus. Okay, so it gets bigger. Okay, anything else about size? Kind of actually like that you're all silent about this one. The other option is looking within a row, right? So we just look within a column. As we move down a column, it gets bigger. Okay? Within a row, we do run into weird exceptions too, but in general, the rule is that it gets smaller, actually, as you go from left to right on the periodic table. Okay? Why? Where are the electrons being placed as I move from boron to carbon? Where's that extra electron going? What orbital? The same type of orbital as the boron. Okay? It's going into a p orbital. Did you already get it?
No.
Oh, never mind. It's going into a p orbital. Well, the p orbitals are all the same size. So if we put the electron in the same orbital, that means its distance from the nucleus is the same. So we wouldn't expect much of a size difference. But what else changes as we move from left to right on the periodic table? The electrons aren't going to help us. It's the number of protons. We've got a stronger nucleus, which means if we put the electron at the exact same distance away from the nucleus, but now we have a stronger nucleus, what happens to the electron? It gets pulled in tighter, which is why when we move left to right on the periodic table, it typically gets smaller. Okay? A lot of time to spend about ultimately doing this. What are we going to say happens on our periodic table, left to right? No size change. Okay? So when we're looking at our periodic table, particularly within individual sub-blocks, so within our P block, the difference in size between carbon and nitrogen is negligible, okay, which means we do not see a size difference between those two. Okay, is there one? Yes, absolutely. Okay. Is it important to our understanding of organic chemistry? No. Okay, so when we're looking within that row, they're all the same. What's another thing we could look at? I listed 3 things. I don't remember what the third thing was. Orbitals, we could look at, oh, is that what the third thing was orbitals? Okay, well, we already talked about that. Okay, what we're seeing on our periodic table is our P block, or at least in our abbreviated version, our P block, and we also have our S block. Why? Because the valence electrons, our outermost electrons, are found either within the S or the P orbitals for those sections. Anybody else still need to sign in? Okay. So those are our primary characteristics of what we're going to end up using the most when we get into our periodic table. Okay. And we do run into kind of exceptions and variations off these things, so we don't really want to attach numbers, which could be a good or a bad thing. Read through some of those online quiz or the email quiz where people told me how they did. There were a significant number of you that were like, yeah, Gen Chem was great because I could deal with the math. And I went, oh crap, I'm sorry. Because if you are really good with math, we're pretty much getting rid of math altogether. It does show up every so often, but for the most part, we come up with some general trends and we hold to those trends. Okay, so there's not a whole lot of math within this. If we take it a step further as far as what we simplify as organic chemists, there's way too many elements, even on this shorthand little version of a periodic table. Okay? My mind gets blown already having to try to think about all of that. So what do organic chemists do? We simplify it even further. Okay? That is pretty much where we're going to exist for organic chemistry, is within those elements, and very little do we venture outside of that. Okay? Typically when we do, we're looking at sulfur or phosphorus, and in second semester we'll pop up with lithium. So really there's only 3 elements on here that have been blacked out that we shouldn't really have blacked out, but boxes are easier to do. Okay? So this is where you want to keep your focus when thinking about organic chemistry and what we're going to work with. Okay? So we've got our orbitals. We know something about where our electrons exist within each of these elements. We know something about their size, and we know something about their electronegativity. So again, maintain your focus on these 10 elements. I think that's close. Okay? Keep it there. You should be doing okay. What happens when we start linking these elements near each other? Okay, well, as we link them, those individual elements start to affect each other. An atom can have an effect on other atoms, and that effect changes its overall chemistry. Okay? That chemistry, because if it changes drastically enough, we go through and we call it something else. We give it a new name. That's our functional groups. So instead of having to memorize a bunch of different elements, we're now telling you to memorize a bunch of different functional groups. Okay? And we will be looking at the chemistry of each of these functional groups throughout the semester, or sorry, year. Okay? This semester, where we're going to stay focused, any ideas? First row, well, that makes it harder to just star all of them. Alkanes, alkyl halides, whoops, come on, alkenes, alkynes, all of those for sure are going to get discussed. Okay, we will probably see a little bit of our alcohols. I'm not positive, but I think we'll see a little bit of our ethers. Okay. For the most part, everything else is second semester. Okay, so those for sure, I expect you to be able to identify within an individual structure. Okay, so you need to be able to recognize those. This is similar to the chart given to you in your textbook as well. I've tried to add some extra information into this, okay, which has to do with how we go through and draw each of these compounds. You'll notice that we've got structures. We've got lines and bonds and atoms and wedges and dashes, which should all vaguely ring a bell from 151 when you looked at Vesper theory. Okay? A new thing that, or maybe not new thing, is that you'll also notice that you see some formulas, some summaries. Those are example formulas. There's an issue with those formulas. They don't directly reference the structure above. Okay, so if we take a look at the alkenes, just keep our focus in there. If I want to make sure that formula matches that structure, I need to change the structure. How would I change the structure? How many carbons does the formula say are there? Okay, how many carbons are shown? That seems reasonable. How many hydrogens are shown in the formula? 4. How many hydrogens are shown in the structure? None. How do we know there's no hydrogen shown? You don't see the H. Okay, so we need to specify that H to make these match up. Okay, so the reason this formula is here is because I want to draw your attention between the relationship between the structure and the formula. Okay, so we now have all of our atoms accounted for. But when you look at that formula, does it say anything about there being a double bond? No. That information becomes implied. Right? And we do a lot of implication when we deal with structures. So you need to be careful that when you look at a formula, there can be hidden information within that. And that hidden information is most commonly based off of being able to draw quickly and efficiently your Lewis structures. Right? Again, 151. Probably the most, or the two most common ones that students seem to get confused by all the time, which is fine, it happens. If we take a look at aldehydes, that functional group, that structure on the left there, is represented by that formula on the right, CHO. Very confusing as to why we picked that format, but that's the way it's drawn. You'll notice when we move to the ketone, we did something similar. Okay, we dropped parentheses around the oxygen. What we're trying to imply is that that oxygen is only bound to the carbon. But to satisfy certain rules within our Lewis structures, there has to be a double bond. Is that double bond shown in the formula? No. Are you responsible for knowing it's there? Yes. Okay. Last one that I'll mention, just because it also seems to throw a big cog in everybody's understanding, is the carboxylic acid, which you will also sometimes see written as CO2H. Okay. Is represented by that structure shown. Okay. You are responsible for all of those pieces and being able to do those extra interpretations. All right, watch out for them when they pop up. Questions? Don't look so depressed. It's not bad yet. Atoms to compounds. Right, so we just looked at examples of functional groups on how we can scale these things up, but how did they come about? Where did we get them from? So if we take two atoms and we bring them close enough to each other in that appropriate distance, what ends up happening is that the electrons from one atom can see the nucleus of the other atom. Why would that be important? Well, if that electron sees another nucleus, what's it going to do to that other nucleus? It's going to try and go there. Right? Which means the electrons now start to inhabit the space between the atoms. Right? If the electrons exist in that place and they're now attracted to opposite nuclei, they can now form a bond, and we can keep those nuclei attached to each other. Okay? There's other options. Maybe instead of seeing that nucleus, it sees the other electron first. What happens? It repels. Like charges repel, and we don't get a bond. So we get this interaction of either forming a favorable interaction, and we form a bond, or a disfavorable one, and they repel away from each other. Okay? What things are going to control that interaction? We could go back. We said there were a couple things that were really important. We could look at size. How big are those atoms? Okay. If those atoms are really big, that's going to change how those electrons can interact with other atoms. What else? Orientation, way to make it too difficult. Let's avoid the orientation argument. Okay, it is absolutely valid, but that definitely brings in the quantum mechanics that we don't want to deal with. polarity is a more complicated aspect of this. We just talked about it. Electronegativity. What is electronegativity? This is a fun one. The ability for an atom to attract. Almost all of you saying are electrons, and unfortunately all of you are not quite right. What kind of electrons? Bonding electrons. Okay, when we're looking at electronegativity, it's really the only ability for an atom to take electrons out of a bond. Okay? It has nothing to do with valence electrons. It has nothing to do with electrons in a vacuum. Okay? Electrons in a vacuum are known as the electron affinity. We don't care about that. We care about looking at how those electrons in a bond are being pushed and pulled around. Okay? So electronegativity becomes really important to us. Okay. So within our interactions, we've got a couple options. We've got this bond where our electrons interact strongly, or we can get not a bond, or this repulsion. Are there other variations within this? Or is it only going to be a bond and not a bond? I don't know, it sounds kind of like a hard question. It is. Okay, think back to Gen Chem. How many types of bonds are there? So I'm hearing covalent, hydrogen, ionic. Is there only one type of bond? No, there's not one type of bond. There's a spectrum of bonds. Okay? And there was a mention of one that's not actually a bond, which brings up another interesting point. Hydrogen bonding, not a bond. But it's an interaction that's not a repulsion. So really what we end up with is now some kind of strong attractive interaction and some kind of no interaction at all. So we've got a balance between those two, and it's the interplay on deciding where do we decide that a strong enough interaction becomes a bond versus something else. Maybe it's an ionic bond. Maybe it's a covalent bond. We have to arbitrarily, and yes, it is arbitrary, decide on those delineations and those definitions. Okay? So there should be 3 common bond types that you remember from 151. Okay? Ionic, polar covalent, and I will always refer to it as covalent, which is why there's parentheses there, but officially it is nonpolar covalent. Okay? So if we're going to look at an interaction on how individual molecules are going to interact with other molecules, we need to be able to look at that atom and say what things are around it. Most atoms are not free-floating on their own. They're in a bond. So I need to know something about those bonds. So if I give you a structure or a bond, what type of bond is that? How do you know that? Okay, good rule of thumb. I like that one. Ionic is a metal and a nonmetal. Is that strictly true? Okay, no is a good answer. Anybody know what the strict definition is? You look at their difference in electronegativity. The symbol for electronegativity is usually, I think it's, what is that, chi? Anybody know? Okay, then we're going to call it chi. If your difference in electronegativity is bigger than 1.7, then it's an ionic bond. So how would you be able to do this? Well, you'd have to have all of your electronegativities for every element you could possibly encounter memorized. Granted, we did just whittle that down to 10, but that's a bit excessive. If you know metal and nonmetal, you're set. It's an ionic bond. All right. How about the polar covalent and nonpolar covalent? You got those definitions memorized? It's a hint. The easier one is the nonpolar covalent. 2 nonmetals, but if I give you the bond of oxygen to hydrogen, polar covalent or nonpolar covalent? Polar covalent. Now, your nonmetal rule didn't quite work. So I'm just going to abbreviate that NM to NM for nonmetals. But that definition is a little bit too narrow. Nonpolar means what? They're sharing their electrons equally. There are no poles. Okay, well, what would be a pole? You just said this compound is polar, right? Or it had a polar covalent bond. Okay, I don't see why it's a polar covalent bond. Any guesses? Could we add something to this to explain why it's a polar covalent bond? Okay, general, oxygen pulls harder than hydrogen. What is oxygen pulling on? The electrons. What electrons? The bonding electrons. Is there a definition that we just discussed that describes an atom's ability to hold bonding electrons? Electronegativity. Oxygen is more electronegative than hydrogen. Where is oxygen on the periodic table? Really darn close to fluorine. Hydrogen really far away from it. Okay? There we go. Based off of our electronegativities, oxygen is taking those electrons. What can we add to this structure to help us see that a little bit easier? A lot of different options. Go through with partial charges. Okay. So to show a partial charge, we just use that lowercase delta, everybody's favorite little symbol. Okay, what charge does each of those build? Negative and a positive. There's our poles. That's why it's polar. Okay. Which one becomes negative? Oxygen becomes negative. How does it become negative? It's pulling the electrons. Next most important aspect of all organic chemistry. Let's show that. How does oxygen pull those electrons? What can I add to this structure to show oxygen's affinity for those electrons? What was that? Yeah. Let's start our arrow where the electrons are. Where are our electrons? Give me a little bit more than in the middle. You're right. In the bond. How do we represent the bond? That solid line. That solid line represents electrons. So my electrons start in that bond. Where do they go? Towards the oxygen. What charge is an electron? Negative. If an atom gets more negative, it becomes more negative. There's our partial negative. Doesn't have to be hard. Okay. Well, if oxygen became more negative by taking the electrons, what happened to the hydrogen? It becomes more positive. Mathematically, does that make sense? I don't know. What charge is an electron? Negative. What happened with the hydrogen? Did it lose or gain electrons? What's the mathematical symbol for loss? Minus. Negative times negative? Positive. That's our emotion every class. Leaving with a positive feeling. Okay. I like the sarcastic laugh. That was nice. Okay, we're looking at a positive here. Okay? So this came back to deciding polar covalent and nonpolar covalent based on electronegativities. So that definition that nobody had memorized, that difference in electronegativity being 1.7 for our ionic, is going to come back for our covalent and our polar covalents. If I trip, it's my fault. Don't worry about it. Okay. Hopefully I won't break anything.
That's why I moved it.
Nonpolar covalent. Nonpolar covalent is, for lack of a better description, same, bound to same. So if I change that hydrogen now to oxygen, what happens? The difference in electronegativity now is nothing. Each of those oxygens are equally pulling on the electrons. Right? That definition is perfect. It works, except it's a little too narrow for us. What's the one extra piece that you need to know? It's a hint. This is organic chemistry. We aren't classifying the amount of bonds at this point. What's that? Someone said it. Carbon. This is organic chemistry. It's all about carbon. Carbon bound to hydrogen. If it was carbon bound to carbon, it's same bound to same. So those are our two classifications for a nonpolar covalent bond. Are there exceptions? Yeah, absolutely. There's always exceptions. Okay, but it gets us close enough. The raw difference for electronegativity, this is what I think may irritate some people, is that this number changes depending on who you talk to, but it seems to fall right around 0.5. So if you look at the difference in electronegativity between carbon and hydrogen, I believe it is 0.1, okay, which puts it in the nonpolar covalent category. So of course now what's the next question? What's our definition for polar covalent?
It's greater than 0.5.
There's someone that's jumping ahead there with the thoughts. It's got to be greater than 1.5. Whoops, yeah, your covalent's got to be less, sorry.
Are those strict rules?
No, they are horribly unstrict. I'm not kidding about, the 1.7 seems to be pretty consistent. The 0.5, I've seen jump all over the place.
Really?
Yeah. Okay, so to identify you have a polar covalent bond, you just need to have the electronegativities memorized. How many of you think I've got all the electronegativities memorized? Really? Only one of you think I got it memorized? I think I've memorized hydrogen. I think I have carbon. I think it's actually 2.1 for hydrogen and 2.5 for carbon. Right. So I can identify one bond, and it's not even the important bond. Right. So what can we use to decide what makes it polar covalent?
Just generally where it's placed on the periodic chart.
Everything else. Okay. That is a lot of our periodic table, but remember, organic chemistry simplified. Our everything else is pretty much coming down to oxygen, nitrogen, and fluorine. Well, actually, it's not just fluorine. It's all of our halogens. Okay, so fluorine, chlorine, bromine, and iodine. Okay? So if you see any one of those elements, it's a polar covalent bond, with the exception of it being bound to itself. Okay? These rough approximations allow you to generate this dipole nature, where when we looked at that OH, what characteristic did we see? Well, we said the oxygen was partially negative, the hydrogen was partially positive. Okay? Can't remember, but I think we talked about this a little bit. All chemistry strives for stability. What makes things stable?
Low energy zone.
What makes things low energy?
Neutral.
Neutral. So when we look at the bond between oxygen and hydrogen, we already can look at that and say that bond is reactive because
It's not.
it's not neutral. We have that negative, we have that positive. Those things can go out and react and do something. Okay, so if you see a much larger structure, what you should be doing is looking at that overall structure and classifying each of these individual bond types into it and saying, that's a nonpolar covalent bond, which means what about its reactivity? It's neutral, which means what about its reactivity? Nothing. I don't expect that bond to interact. So you can start to eliminate reactivities by pulling some of this information out. Okay, so it comes back to these bond characteristics. Is it as simple as just looking at the bond? No. Classic example, I'm going to erase everything. That's not the classic example, but polar bond, nonpolar bond. Polar because it's not same bound to same. They're two nonmetals, so it's a polar covalent bond, which means the oxygen is negative, the carbon is positive. So we would expect reactivity. So let me finish this structure out. What reactivity do we expect? What compound is this? CO2. What's the reactivity of CO2? Very, very little. Why? How do we know that to be true? Not only is it everywhere, what's one of our big issues as far as science goes? Global warming, which was due to Carbon dioxide. If carbon dioxide was reactive, would it be built up in our atmosphere? Would it be causing any kind of greenhouse gas issue? No, the reactivity for this compound is ridiculously low. But if we look at the bonding characteristics here, we would say it's reactive. It has these partial charges. Why is it not? We're starting to...
Too strong double bonds.
I wouldn't even go with that.
The dipoles cancel.
The dipoles cancel each other out. The negative oxygens pulling electrons opposite directions cancel each other, and the reactivity virtually goes to nothing. Okay? So having an understanding of just these bond classifications doesn't help us. We also have to know something about its shape. But how do we get to shape? We need to know something about how those atoms are connected. Is there a theory that explains how atoms are connected? Vesper gives you shape. What's the theory that shows how bonds form? We connect an atom to an atom. You were asking earlier about double bonds versus single bonds. What's the theory that explains that? Famous chemist. Begins with an L. Lewis. Linus, not a bad idea. He's actually probably more famous. We're looking at Lewis structures. Okay, so we're going to turn this into a short little quiz. I am